And as always, our recordings of our virtual meetups will be available on YouTube about a week after the meetup. We'll post the message on the meetup when the recording is ready. So I'm very pleased to introduce our speaker today, Rainer Dronzek. Rainer is a fellow solution architect in the simulation and decision science practice at Engineering USA, a provider of digital transformation technology, solutions, and services headquartered in Chicago. He has held technical and leadership positions in the aerospace, oil and gas, software, and consulting industries. He was first introduced to simulation modeling on the Space Shuttle program at the Kennedy Space Center and has been involved ever since. His simulation project work covers a wide range of industries using many different simulation applications. He has managed simulation projects and standing teams providing modeling services, founded an independent simulation consulting firm, collaborated with universities and professional societies, and organized simulation modeling events and conferences. And then for questions, feel free to put them in the chat. And then you can also use the raise your hand feature. And then Rainer will get to your question, or I'll also indicate there's a question. Okay, so now I'm very happy to pass it off to Rainer. And yeah, Rainer, you can take it away.
Thanks, Olivia. Absolutely feel free to chime in with questions. We have a small enough group where I think we can make this very interactive. So thanks for spending your evening with me, or your happy hour. And my talk today is going to focus on simulation modeling. And I know you've had a couple talks within the past few years. I know one of the folks from AnyLogic talked about AI integration with a tool called AnyLogic and dove into the code. My intent is to give you a little bit higher level view, but we'll also kind of peek under the hood, as I mentioned in the abstract. So peppered throughout the presentation, I will show you simulation model demonstrations from a couple different applications. But I want to kind of talk about kind of an introduction to simulation modeling. We'll talk about a couple of key terminology points that are buzzwords that are very common in the industry and in some cases may cause some confusion. So I just want to level set on what I mean and what we mean in the simulation modeling world by a digital twin in Industry 4.0. We'll talk about a little bit the art versus the science of simulation model. I'll give you a list of all the software packages, or most of the software packages that are out there, both commercially available and open source. And then talk about a couple things that are relatively new in the industry. One is hybrid modeling, and the second is integration with artificial intelligence. So let's get started. The first is to make sure that we're all talking the same language, because simulation and model are both very generic terms that can cover lots of different things. And so sometimes when I talk with folks about simulators, they think of battlefield tank simulators, healthcare simulators, aircraft simulators, and things like that. That's not what we're going to be talking about today. And if we talk about models, there's lots of different types of models, ranging from mental models to Excel spreadsheets to formulas. One of the common ones that, and I don't want to say causes some confusion, but is a differentiator within our industry would be physics-based models, where we're doing things like computational fluid dynamics, actually modeling the physics of something. That's not what we're going to be talking about here either. Our focus will be on kind of process-based simulation models. So I'm going to start and actually just jump into a simulation. I'm going to start with and use in a couple different ways a distribution center simulation model. and my computer is slowing down, so hopefully this will work good. So this happens to be a tool called AnyLogic. I'm going to use two different tools today during the talk. I'll also show you a list of all the other ones that are out there. And just want to confirm, can you still see my screen? Because mine is looking different. Okay, got it. I see Olivia nodding. Thank you. So this is the development environment for a tool called AnyLogic. All the tools that are basically out there are what I call general purpose simulation modeling tools. So they're intended to allow you to model virtually anything. Some of them have specialized industries that they're best for, but in most cases, they can be applied to virtually any process. A lot of times the distinction is the graphics that come with the package that make it a little more easier to communicate a particular topic within a particular industry. But in general, they're general purpose simulation modeling tools. So I'm just gonna run this model. And then we'll walk through what you're seeing. So the splash screen is here. And you can see this particular tool. One of the interesting things is it gives you the ability to design in interaction with the actual animation. So I could pre-select certain parameters for this particular model as I enter in this splash screen. And I'm going to press the run button. And what you'll see is the model appear in a new screen. And you can see that there's movement. So many times people confuse this with, oh, it's a animation program. True, it does give you the ability to animate, but more importantly, there's statistics and details and process underneath here that are the real value with these type of tools. So just by way of kind of orientation, what you're seeing is a simplistic distribution center where I have on the right-hand side, I have trucks coming in, they're unloading pallets. The pallets are moved to storage locations by forklifts. And then, so that's the inbound. The outbound, you can see the trucks that are picking up from the loading dock. So the forklifts are assembling orders that are then moved into the truck. And so what this model is intended to look at is kind of the schedules of the trucks that are coming in, the number of forklifts that I have, how long it takes to pick things from the rack, going into an assembly area, and then the outbound schedule for the truck. So every simulation project has some type of objective around which the model is built, and it's intended to answer certain questions that you might have. And so that'll be one of the things that we talk about later on successful projects is making sure that you're very clear on what the objective for the project is so that you can build the model appropriately. You can see this is most applications these days give you the ability to do both 2D and 3D. Obviously, 3D is a lot more pleasing and call it eye candy. It does nothing for the accuracy of the simulation. It's more for helping with the storytelling. And I can kind of zoom in on a couple particular areas. And again, you can see with this particular tool, as well as this particular model, I have the ability to change parameters. So I could change the number of forklifts. I could change some of the times it takes to do things. I could change capacities. So in this case, this type of a model, often what somebody's looking at would be, if this is a new process, how many forklifts do I need to buy? How many forklifts and forklift drivers do I need to be able to support this operation? What happens if my volume increases next month? If I double my volume, where will the bottleneck be and where will the bottleneck move to? That's probably one of the keys. So typically simulation modeling comes out of the industrial engineering discipline in schools. That's typically where it's taught, sometimes in operations research as well. And I would argue that if there's an industrial engineer at this facility, they know where the bottleneck is. It's pretty simple to walk out on the floor and see where it is. The question is, if you make a change to the process, where does the bottleneck move to? And that can get complex to predict. And that's one of the benefits of simulation modeling. So in addition to the visualization, I'm also interested in what the statistics are. So I'm going to speed this model up a little bit just to kind of generate some of this statistics. And these are kind of a couple of the traditional and common things that I might look at. So how long does it take to do things? So what's the processing time within each of these steps in the process? So unloading, assembling an order, picking a pallet from a storage location, those type of things. And utilization is an indication of how busy is something. It could be a person, it could be a forklift, it could be space. Virtually any parameter that I define that has kind of a fixed capacity or is some type of a constraint on the system, I'm going to look at the utilization. So you can see my forklifts are pretty well utilized right now, so I don't have a lot of wiggle room. And more than likely, if I added more forklifts, it's quite possible that my processing time would be reduced because I'm at 100% utilization. So I'm using most of the forklifts that I have. The loading docks, they're at about 60% utilization, so there's still more space there. So that might be one of the things that I might want to look at is if I'm trying to optimize my process. And in addition to kind of the 2D and 3D look of things, I can also customize the way I want to present information. So this is more of an abstract view that's showing the kind of the key process steps and how many things are in each of those steps. So you can see I have a lot of things in queue right now. And this appears to be one of the areas that I might want to focus on, which would be to try and reduce this queue and balance these queues out, the amount of objects that are being processed throughout the system. So I can create these custom animations and abstract representations of systems or process rather than just relying on, you know, a CAD-based or a very detailed process look. And then I have the ability to kind of move in and out and have camera views and camera angles and hone in on particular things. So that's an example of a simulation model. Again, this one happens to be AnyLogic, and it's a distribution center. Typically what you'll see, the use for this would be from the folks that are managing the distribution center. So if I have a question, if I'm going to insert new automation, I might build a simulation to help justify or understand if that actually is the true bottleneck. So if I'm going to spend $1 million on an automated storage and retrieval system, I want to make sure that I'm spending that money wisely, that that actually is the bottleneck, and that I'm accounting for what performance improvement I'm going to see if I install that. So I can build a simulation of the facility and do it that way. Oftentimes, on the other side, we also have vendors that are proposing or building these systems for a client. They will use the simulation model to identify how well their system works. And sometimes a client will require a simulation, especially in material handling type systems and production systems like, you know, manufacturing lines. Olivia gave you my background, just a couple of things. This dates me, so I go back to the days of punch cards and paper tape readers. So just to give you an idea of my vintage. And as Olivia mentioned, I was first introduced, I worked on the space shuttle program at the Kennedy Space Center, and we had an IT group that had lots of money, and they were the first people within our company that got a hold of simulation modeling tools and actually did some models of the processing of payloads for the space station. And so that's where I first learned about it. And then a couple of years later, got into it, you know, in actually within the aerospace industry, doing some modeling for lean manufacturing operations on the Joint Strike Fighter. And then consulted in a lot of different industries, doing manufacturing projects, kind of a lot of different areas. And for 5 years, I led the operations research group at the McDonald's Innovation Center. We did things other than simulation modeling, but we did use simulation to help understand the operations in the restaurants, as well as the flow of customers and staff and vehicles and things like that. So it was a pretty powerful tool for helping to improve operations there. And these days I'm working for a company called Engineering USA. We're a consulting firm working on a lot of different projects, mainly manufacturing oriented. So for example, a big one right now looking at the operations around the maintenance and support of Navy fleets activities. Engineering USA, basically, we're a consulting firm focused on the digital transformation. We're going to talk a little bit about this later when we talk about Industry 4.0. But the whole idea is moving from paper and from disparate software systems that might be across an organization in the life cycle of a product, from design through the delivery of the customer, and trying to get that single digital thread where we're sharing information and making the best use of digital information throughout the entire life cycle of that product. So again, just to level set, this is my definition of simulation modeling, and most practitioners will probably agree with most of this. So it's creating a computer-based dynamic digital representation of a business system or process, and then conducting experiments using this digital representation to help you analyze and predict performance. And it's an executable model that we're building. So within the simulation package, I have the ability to kind of to define rules. What happens in the process. So if you think about it, start with the process flow, and then what are all the decisions that need to be made through that process? Those would be built into the simulation model. We're moving through time. That's one of the characteristics of a simulation model versus other techniques, is we can actually move the simulation through time. And then we're able to also look at outputs as the simulation is running and observe them visually as well. So basically, I build a model. I have a series of inputs that I use to drive that model. I run the model, and then I observe both electronically and visually the things that trajectory as the model proceeds and things change over time. And then I can rerun the model, change the inputs, see what happens, and then compare the results to understand is something better or worse when I change an input. And it's dynamic. This is one of the big differentiators between this analysis technique and other analysis techniques as well. Again, through time, changing conditions over time are accounted for, and variation in the process is accounted for. So our company is headquartered in Chicago. I happen to be in the Madison, Wisconsin area. Kind of been associated with UW-Madison, and so I always have to advertise UW-Madison through this quote: all models are wrong, and they are. We have to recognize that, but some are useful, and we have to keep in mind the context of the model as we're putting things together. And this leads in a little bit later when we're going to talk about the art and science of simulation modeling. So why would I use a simulation model? Well, if I think about it, if I have a problem to solve, and it can be in virtually any industry, I could actually, create a mock-up or implement something and see what happens, which potentially could be even catastrophic. And so I'd like to be able to test what I'm trying to do offline. And so I move from the real world into the digital world, the world of models. I create a model of my system, and then I test the solutions that I propose to implement on this computerized version. And only then do I move that solution into the real world. So now I have a little bit of an insurance policy that what I've proposed will actually help and won't harm. So simulation goes back to queuing theory in many cases, and so just as a to highlight one of the benefits of simulation modeling where we're taking variation into account, we'll just start with the simple bank teller problem where although these days it's becoming less and less common, but I walk into a bank, I walk up to a teller, I do something, I make a deposit, I get some cash, I do some other transaction, and then I leave. So a very simplistic queuing theory problem. And I'm going to keep it simple and say, okay, I'm going to build a model of this, and I'm going to define the number of tellers that are there, how long it takes to do a transaction, and how often customers are coming into the system. And what I'm going to look at is how long does the customer spend in the bank, how many customers are in queue, and what's the utilization or how busy is that teller. And in this particular case, I'm just going to make it really simple. I'm going to assume one teller, the transaction time for every customer is exactly 5 minutes, and the customers arrive exactly every 5 minutes as well. So if I look at the results of that simulation, if I build a model, of course, you can predict what that's going to be. My transaction time is 5 minutes. The amount of time that the customer spends in the bank, and I'm making an assumption here, I'm not including walking time and things like that. So would be 5 minutes because every transaction is the same amount of time. There's never a queue because I never have to build up a queue because there's always time available for that teller to serve somebody. So I never have a queue, and that teller utilization is 100%. They're always busy. So what happens if I start accounting for variation in the process? So rather than a transaction time of 5 minutes, I'm going to keep the average of 5 minutes, but it's actually going to be somewhere equally likely between 4 and 6 minutes. So that's a uniform distribution. So you can see now I'm going to start to see some buildup. I'm going to see queue times increasing. I should say the number of people in queue. My teller utilization has dropped a little bit, and you can see that the average time now goes from 5 up to 7.4 minutes. And the worst case is one of my customers spent 11.4 minutes. So now I'm starting to see the impact of that variation and kind of the application of queuing theory. Now, if I move to a transaction time of 1 to 9 minutes, again, this is a uniform distribution, I can see the situation gets worse. Teller utilization is not too bad. And of course, I have some customers that get through the line very quickly, down to 1.2 minutes. But the worst case is one of my customers spent 30.4 minutes. And this is because of the buildup of that variation in the buildup of queues, the dynamic changing of those queues over time. And so that's kind of the key that I might look for here is, as I'm looking at this system, what do I do? Well, let me add some more tellers and see what happens there. So my teller utilization is going to drop if I would add a next teller, but now I can look at it from the customer's perspective and say, yeah, I can get through the system quicker. But the reality is that was a horribly simplistic model. If you've been to a bank, you know that you can have a ton of other variables that I need to take into account if I'm in charge of this process. So obviously, customers don't arrive every 5 minutes on a metronome. They have some type of arrival pattern. For example, when I was at McDonald's, we even looked at things like if the restaurant happened to be at an intersection where there was an arrow, a left turn arrow. So rather than a steady arrival of cars in the drive-through, now you have bursts of cars coming in. And if you account for the total experience time when somebody gets in line, that becomes a big factor in how I'm trying to look at the process performance. So you can see each step of the process, we can have a lot of different things from behaviors like customers jumping between queues. If I have multiple queues, how do I account for that? Not only do I have tellers, but I have ATM machines. I have multitasking, I have priorities, I have differences in skill. Do I account for breaks? So I can easily build a really detailed model to represent what is actually happening within the system. So let me show you, this is a different tool. This is a tool from Siemens. It's Siemens Technomatics, tool called Plant Simulation. It's been around quite a while, and it's mainly focused on manufacturing operations. And it's also part of a suite of tools, as I mentioned, this digital thread that carries us all the way from the design all the way to delivery to the customer. This is one of those tools that helps with that. Oops, and I just missed that there. So here's an example of a dairy operation. So one of the things you're going to see is the development environment where I'm dragging and dropping objects. And this is typically how you're going to build a model. You will drag and drop objects and then open up the dialog boxes within, set certain parameters, and then also write code as required, for example, with complex decision rules. And you can see this is a little bit more high fidelity animation, which may or may not be accounted for depending on what the end use for the model is. And you can see it's moving through some of the predefined types of data. And here's some examples on actually going into those dialog boxes and changing shift operations, for example, to see what the impact on the process is if I add or reduce hours in my shift. In this particular process, the previous kind of the teller operation and the warehouse operation was a discrete operation, so things moving through in chunks of time. This is a continuous operation that you might see in oil and gas, food manufacturing, some areas where I have a constant and continuous flow of things going through pipes, for example, that I can model as well. So when I do a simulation project, ideally what you do is you go through a pretty structured process, just like you would do for coding or any other development activity. And the first thing you do is you document. You understand what the objective of the project is, because then that'll help you design the proper simulation model. You understand the scope. So when do I start and when do I stop? How do I bound the process that I'm trying to model? And typically what we'll do is, it's called different things in different companies, but some type of a simulation design specification that's a living document. Starts up front in the early phases of the process to say, yes, these are all the things we agree to. And as the model matures, so does the simulation design specification, just to make sure that we have an understanding and agreement of what the simulation model is doing. Then after I understand and design, then I'm going to build the simulation model. I'm going to build the user interface and the preprocessors that allow me to get data into the model, and then the dashboards and other things, including post-processors maybe, where I'm going to understand the outputs of the model. And those are going to be those KPIs that are that I've identified up front when I talk about what the objectives are. Then I'm going to verify and validate the model. This is one of the most critical steps. Verification means, as I'm sure everybody in this call is aware, within their own world, would be making sure I've coded the model correctly. So are there errors in the model? Do I have problems between the model and what was actually designed? So that's kind of the coding process. But then I'm also going to validate after I'm making sure that the model is structured correctly. Now I just have to make sure that it accurately represents the system, because it's possible when I've designed the model, I haven't accounted for something that results in the model not being a good representation of what's really happening. And that's really important, because if the people that are using the model don't believe that the baseline or that it's accurately representing what's happening now, when I start making changes to the model and getting these results, sometimes often very counterintuitive, the believability will be very difficult to follow. And so it's very important that we verify and then validate the model, and then we start using for analysis. So as we talked about before, I can run the model, then it runs through time. And then I get things like output results. I have visualizations to help understand the system. I can start doing what if experiments. So let me change some parameters and see what happens. I can compare those scenarios and see, yes, A is better than B or not for whatever it is. And I talked earlier about an insurance policy, so I can actually start looking at risk. What's the risk of doing something? And I can use this to help quantify what that risk might be if I'm going to apply something. And that's where that process variation comes in. You can see that box plot is intended to show that when I run a simulation model, what I'm going to get out is a range of values with a likely value. And that's where I need to understand kind of the statistics behind the simulation as well. And then lastly, I can start optimizing. So not only am I going to kind of manually change the dials and see what happens, but now I can actually use some tools to say, let me hone in on the best solution. What's the right number of forklifts to have? Let me optimize the number of forklifts based on some parameters that I set that I'm trying to optimize toward that objective function. So just some examples of why I would want to simulate. One of the key ones is these models they become complex very quickly. That's because the systems that we're modeling are complex, and so kind of a spreadsheet approach is often not good enough to be able to understand not only complex interactions but also adaptive systems. So systems that are dynamic and change over time based on the conditions that they're experiencing. So that's one of the ideal uses for simulation. I can use the model to test things that would be impossible. So for example, gosh, just during the recent COVID outbreaks, some of the things that people are looking at would be, if I need to do a large quantity of vaccinations, it'd be kind of difficult to set up a trial to see how that works. I can use this offline simulation to design the best way to vaccinate a very large number of people through, vehicles moving into a large facility. I know that's what we had here locally. And so using that simulation to test things that you wouldn't be able to do, shooter situations, large volumes of things, catastrophic events, all things that are easily tested within a simulation model where it might be more difficult to do in a real system. So you can see some of the examples here on some of the things that would be advantages for why you would use a simulation model. So we've all seen these kind of multiple categories, 3 or 4 categories of types of data analytics. So the nice thing about simulation modeling is that it applies to all of them. So descriptive, describing what has happened. I can build a model of a system and then I can help people understand. It could be used for training. It could be used to visualize something that might be difficult to visualize in a real system. So simulation can be used for descriptive analytics. I can use it for diagnostic analytics. So why did something happen? I can kind of peel the onion within my simulation and say, yes, I had a backup because my teller was 100% busy, and so that's why the queue was building. I'd be able to diagnose that. Then I can predict what happens if I change the system. Where does the bottleneck move to if I change some of the process parameters? And then lastly, kind of prescriptive. Not only what will happen, but what's the best action I should be taking? And that would be using those optimization techniques to hone in on the optimal solution based on profit, on time, whatever is important in the objective of the simulation. So here's a little bit of a different example. I'm going to show you a supply chain. And in this case, it's very, very simplistic, but I think it kind of illustrates a couple of cool features that you might use a simulation for. So this is so I'm going to do this because something's blocking. What I have is 3 manufacturing sites, Chicago, Pittsburgh, and Nashville, serving a series of distribution sites. And what these factories they're producing, they're being transported through a truck network. And the cool thing is I'm actually using a GIS road network as part of this simulation model. So these trucks are following the road network to get from point A to point B. So some of the things that I might be looking at would be, what's the production rate for each of these here? The fleet utilization. So this is how busy are the trucks? And so I might, if I'm the transportation manager, I might want to optimize the usage of my fleet. And then the wait time. So how long are distributors waiting for their product to arrive? And so you can see, just as a quick glimpse, my Pittsburgh fleet is 100% utilized. So this is an area that I might want to look at because I might be having some capacity constraints. So as I showed you before, one of the things that I could do is I could, in this case, I have sliders on here. So I'm going to move this down just a hair. You can see I'm at 100%. If I go back to the animation and I now increase the number of trucks that I have in Pittsburgh, voila, I should see my, my fleet utilization be reduced. And you'll also notice that my wait for products is also being reduced. So the fleet size in Pittsburgh was a bottleneck for my system. And by increasing the number of vehicles, I was now able to kind of even out that that utilization rate and also improve the kind of the customer satisfaction and the delivery times for the customer. So just a quick example of how I might use the simulation for analysis in a supply chain, and then also integrate with a GIS system.
Oh, Rainer, we have a question in the chat.
Yes. How do we incorporate the speed limit of the roads and let the trucks follow the speeds of the road? So this particular model is following the road networks. And what we're doing is we're limiting the speed of each individual truck for this particular simplistic model to some speed limit. What we would do is change the model to move more towards like a Google map or a Yahoo map, whatever you use, a TomTom to get from point A to point B. If the GIS system supports that, then I could do that as well. So now the truck is going to have some maximum speed, but it'll also decrease and follow the speed limit, for example. And I could build all kinds of decision rules in there as long as I had the data available in the GIS network to be able to do that. Does that answer your question, Siva? Cool. Who can tell me what the most popular modeling tool is? Or guess? Any guesses?
Oh, wait.
Excel. So, and which is not a bad thing. So from a consulting perspective, when we come in and somebody has realized that they've reached the limit of what they can do and have a lot of information in Excel, it is an advantage because that means they've got to start on the data that we need to drive the model. And so, yeah, oftentimes you'll see people using Excel for analyzing a process and modeling that process. And actually, I want to make sure because my in a second, I'll give you a list of simulation tools, but there's 3 paradigms on how you develop models. And there's tools that are focused on each of those. The first is system dynamics, been around a long time. Jay Forrester started it back in the 50s. And it's looking at the kind of the relationship between systems and the flow of things. It could be people, it could be ideas, it could be information, it could be products, whatever it might be. And they're modeled at a aggregated level. They're not modeled individually. And I have these feedback loops that are driving the system behavior. The second is a discrete event simulation, very process focused. The warehouse model that I showed you is an example of that. And agent-based is probably the newer, and what it's looking at is agents moving through a system and interacting between themselves and with the environment. So a little bit of different approach to how you build a model. And each of these paradigms has kind of the visual language. Most tools these days have some type of graphical user interface that you use to build the model. So with system dynamics, we're using the stock and flow diagrams. So it's showing the movement, it's showing feedback loops and kind of parameters and values embedded within each of those. Discrete event is very process flowchart based. So I'm going to drag and drop process blocks and then define the parameters for each of those. And then agent based. Where I use state charts, which are a fantastic way to model. And we'll talk a little bit later about hybrid models. And I can also use action charts and kind of like decision trees for those as well. And then typically, most of the simulation tools will have a really easy to use drag and drop interface. And then when you need to get a little bit more complex, there'll be some type of a scripting language. So AnyLogic uses Java. And PlantSim, the other tool that I showed you, uses a proprietary language called SimTalk. And virtually every simulation tool has some type of a language that they use where you're actually going to be writing code when the easy way of radio buttons or selecting things and using pull downs needs to be taken a step further. Here's a list of kind of the main simulation tools that you'll see out there that are commercially available. I mentioned I've been showing you AnyLogic and PlantSim, but there's lots of others out there as well. There's also open source simulation tools. Probably the most common, I'll show you an example, would be SymPy, which is a set of libraries for Python to build models. But these are some of the other tools that are out there, open source, typically out of universities or government institutions. So sets of libraries to build models like NetLogo and Swarm and Repast are agent-based modeling tools. So I won't go into the details, one, because I can't. I'm not a programmer, but I'm dangerous enough to point people in the right direction. So there's a link here that will get you to one example of using SymPy, but basically you can see here's the code that's used, and here is just they actually developed a visualization of a process as well. So you can see things moving through a process, getting in queue, spending time, and then also separately having the ability to kind of output the results of the simulation as well. So it's a really good free open source way to build a queuing theory model using Python. I did that already. So one of the things you're going to hear, maybe you've heard a lot about, is this idea of a digital twin. And the idea is to have a digital representation of an actual system that I can use to do a lot of different things. So I can monitor it, I can do what-if scenarios, I can help improve performance. And it's this digital copy that I can visualize the real system, I can interact with the digital version of it, and I can experiment. And again, kind of in this risk-free environment, offline environment, before I make any changes to the real system. And there's typically three pillars around digital twins. The first is between the model and the actual system, you have to have some level of connectivity, two-way. So not only is the model kind of looking at the system, but the system is providing information on its state back to the model. And typically that's through IoT devices, so Internet of Things devices, connected sensors, for example, that are streaming data back to the simulation. I have a digital copy, so obviously, we're building these computerized models, and I have to have some level of intelligence to be able to understand what's going on, what's driving the system, and then what are the sensors telling me back again. So that's where I build the rules into the model itself. So this is generic digital twin, and we're going to talk about, and the other important thing is that it's real time or near real time. So I need to be able to sync up my model to what's actually happening to say, yes, they're exactly the same now, so I've got the latest information. When we talk about simulation-based digital twins, arguably we've been doing simulation for a long time, and no one called it a digital twin. because it wasn't a digital twin, because typically we didn't have it connected to a live system. So these days I can have a simulation model that's a digital twin if I do have that connectivity, but not necessarily every simulation is a digital twin. So the essential characteristics are I need to have a representation of a simulation model of an actual operational system. Could be a warehouse, it could be a machine, it could be a process. And I need to synchronize the model to the real system. So I press run and I go and I suck data from the real system and say, okay, these are the queues right now. This is all the information that's there. These are the machines that are up. These are the machines that are down. These are the number of packages in my warehouse, whatever it might be. Then I can start using the simulation to make decisions and possibly control the system as well. So we've got to have that connectivity between the two. The model needs to be flexible enough to be able to change parameters on the fly as I do my what if analysis. And probably the most important, and this is why we probably didn't do a lot of digital twinning in the past, is I need to have that high speed connectivity between the simulation and the real system. And so you've got to have that speed, and not only speed of the connection, but also speed of the simulation, speed of the IoT devices that we can quickly do that what if analysis in near real time.
We have one more question in the chat.
Yep. Emulation versus digital twin. Great question, and I'm gonna show you an emulation, and I realize I'm running a little bit long here, but I'm going to show you the difference. So a digital twin will always be some level of abstraction, and I'm going to bypass this example. And an emulation is going to get closer to the real system than probably a digital twin or a simulation model will be, because that's when we get into the art and science of simulation, is understanding what that abstraction level is. Just real briefly, just a reminder of what Industry 4.0 is. So here's a list of the industrial revolutions, the four, and currently we're at what's often called kind of the IoT level. So this is the digital representation of things, and using that digital representation to link the physical world to the virtual world. And I'm going to skip by, no, I won't. I'm going to do this real quick. So if we think about the physical world, I've got people, assets, and products. And the digital world, I'm going to be designing things. I'm going to be producing those things, and I'm going to give them to someone that they're going to experience the thing as they're using it. Could be a product, could be a phone that I'm going to design. And what I'd like to do is have this digital thread through all of these. Right now, often we have disparate systems or no systems between each of these elements of the product lifecycle. And what we're getting to is, as I'm designing something, I'm carrying that design information through the production process all the way through that to that end user. And as I'm incorporating the supply chain, so between design and produce and design and deliver to the end customer, I've got a supply chain, and I'm going to create a digital representation of that supply chain as well. So now I have model-based supply chain. And each of these, I can develop a digital twin of those. I can use software tools. I can use manufacturing execution systems. I can use product lifecycle management. I could be using ERP systems to control my production and my ordering and planning. All those things, ideally, I connect them all. I use the same set of digital information. And then on top of that, here's where we come in on the simulation side of things, as well as other areas, would be we can use these digital twins to help make decisions in both strategic and kind of real-time basis. And I can go through this digital transformation as well. I'm going to hold off on that. Real quick, so this is, to me, the most fascinating part of simulation. The science, a friend of mine used to call it, I can code. He called it the clicking and clacking on the keyboard. I can build statistics in. I can do validation and things like that. That's the science part of it. But the real part of it is the art. This is where the experience comes in. So how do I manage a project? How do I build a model that is to the right level of detail to be able to answer the questions? How do I communicate the results? I can have the best model in the world, but if I can't communicate the results out of it, it's a worthless model. And then how do I also understand what the user needs, and how do I design that user experience? And one of the keys is developing that level of abstraction. So if we talk about Einstein, his quote, "A model should be as simple as possible, yet no simpler." Again, this is a paraphrase of the actual quote at the bottom, but that's the genius, and that's where the art comes in. How do I build a model that's robust enough, yet I don't go into too much detail, because more detail means more coding, more data, more verification, more validation, more communication, everything. There's an expense and overhead on top of that, the more detail I build into it. So what's the right level? How do I design that in? I won't go through an example because we're running out of time, but it's easy to build a model that has too much detail into it. And it can also be easy to build a model that doesn't have enough detail, where I may not account for certain things that are really critical in the process that I need to build into the analysis. And so, again, this is where that art comes in, and it's also evolutionary as the model progresses. So I start simplistically, ideally, and then I build detail in as I start analyzing the model and understanding where I might have differences between the real system and the modeled system. Just some examples on how I, again, might need to build details into a simulation. But this one I think is real critical. So this is to the earlier question, this is getting towards emulation. So with PlantSim, I probably used a simulation model to verify that a robot is the right thing to put into this cell. And I quantified the impact that the robot could have. I said, yes, it makes sense to put it here. I can improve my throughput by adding a robot. But then I can go to the next level, and this is a tool called Process Simulate, where not only am I looking at the nature of kind of the throughput, but I'm actually looking at the kinematics and the physical representation of the system to understand collision avoidance, how actuators are working. There's people in the process, so now I can start doing ergonomic analysis. So I'm taking that process level model and adding more maturity to it, and getting to more levels of detail. So this is a really great example of that digital thread, where I start with process model and I use that information, and now I plug it into a more robust tool that focuses not only on understanding more details about the process, but I can actually create this emulation of the robot. So now I can test the code that I write to control the robot. I can test it with a virtual robot. So that's where the emulation comes in. And I can do kind of that validation and commissioning process. So I can kind of test the software against a virtual system and vice versa. The other thing I think that is coming up that's important is this idea of hybrid architecture. So we talked about agent-based, system dynamics, and discrete event. Typically, they've been kind of independent paradigms, but now we have tools that allow us to have, for example, a discrete event process running inside of an agent moving through a system. So now we're harnessing the power of these paradigms and creating these hybrid models that give us better capability. So for example, in healthcare, I might have a process where a patient is going through the process, let's say in an emergency department, yet at the same time, I have an agent that's controlling their continuous behavior, things like my temperature is changing over time, and my condition is worsening as I'm moving through this very discrete process. And so now I can use both of these approaches to help better model what's going on within that environment. And lastly, the linkage to artificial intelligence. And so we have a whole community of AI folks that are building AI algorithms that are discovering that simulation can be a really powerful tool to augment what they're doing. And so, for example, one of the things you can do is you can build a model of a system to create the synthetic data. And this is a brain down at the bottom. So the person that's developing the algorithm or the brain needs data to be able to do that. And so rather than going out and trying to collect data and correcting data that comes from a real system, I can start with a model that generates synthetic data that we know is clean, good, and covers all possible scenarios. And that's what I'm using when I'm developing the algorithm. Then I can actually use that simulation to train the brain. So this is where there was another talk for PyData Chicago from the Anylogic folks, where they've created a connector between Bonsai, for example, and Pathminder, two environments for developing AI reinforcement learning algorithms. So now I can use that simulation to help train the brain. And finally, I can actually take that brain that was trained and insert it back into the simulation of the environment. And now I can say, yes, this brain is working well with this in an environment. And if I have a change in the process, I can change the simulation, take that brain, put it back into the environment and say, oops, this brain needs to be updated. I need to go back through another training and learning environment and retrain that brain before I put it back into the system, because something in the system has changed. So hybrid models and AI are kind of the two latest things that are going on. And then I'll just show you one last example. I talked about healthcare. This is actually a trauma center. This happens to be Norwalk Hospital in Norwalk, Connecticut. That was done a long time ago. Still a really great example of using simulation in healthcare. So in this case, we've probably all been to an emergency department. So I've got patients coming in, both through ambulance, so emergent care, and then a waiting room, going through registration and triage. I've got express care that are open certain hours of the day. I have behavioral care for folks with behavioral care issues that require special treatment and special staff. I've got ancillary services like X-ray. And so I'm looking at the flow of individual patients moving through the system, and I have the ability to interact and say, let me change the number of staff, let me change the number of doctors that I have, let me change the hours of operation of express care, for example. And I can understand what the impact is on the length of stay for customers, for patients. So just a really good example of how simulation can be used to help improve operations. So in this case, what it might be is maybe I'm looking at how many X-ray suites do I need for a new operation. So now I can ramp up if I'm expecting increased volume over the next couple of years. An X-ray suite costs you, $1 to $2 million at least. So I want to make sure and make the right decision. I can do it offline with the simulation before I actually implement it. So I rushed. I apologize for running late. I appreciate your time. And I see there's a couple questions. Yes, here's my contact information. If you have any questions after the sessions, just let me know. And I appreciate you sticking with me, and hope you have a good rest of your evening.
Yeah, great. Well, thank you so much, Rainer. That was really interesting to learn. Yeah, I remember just learning about operations research recently. So that was cool to see stuff in simulation. Okay.
All right.
Thanks. Yeah.
Thank you, everybody. Have a good evening.
Thank you.